Have you ever just looked around, at everything and wondered, like, how it all works? From, like, the tiniest little particles to, well, huge things like galaxies. It sometimes feels kind of random, doesn't it? Like it's all just chaos with no real reason behind it.
I totally get that. I mean, it's a pretty natural way to feel. You see, for ages, we've been trying to understand these super complex systems, things like the quantum world or even just how heat spreads using mainly statistics. It's all about probabilities, chances, and averages.
Yeah, it's like we try to make sense of the unpredictability using these sophisticated math tools like, say, random matrix theory. Right. But, and this is where it gets interesting, what if the unpredictability, the randomness, isn't the whole picture?
That's a great question, and that's precisely what this paper we're diving into today is all about. It's titled Fractal Resonance Cognition, a Framework for Complex Systems Analysis. And it suggests there might be a hidden order, a structure beneath all that seeming chaos.
So not just random noise, Ben. Tell me more about this, what they call it.
Fractal Resonance Cognition, or FRC for short. It basically offers a completely different perspective. Instead of focusing on randomness, it proposes that much of this complexity we see arises from self-similar structures that kind of interact with each other in a resonant way. Less like rolling dice and more like a bunch of intricate gears all meshing and turning together.
Self-similar structures interacting in a resonant way. Okay, I'm intrigued, but let's break that down a bit.
Sure.
So if I'm getting this right, the heart of FRC is that these systems, as complex as they appear, aren't just a jumbled mess.
Right.
Instead, they're organized by, and I'm quoting the paper here, vortex-like attractor structures. And these structures, they have this fractal nature, meaning they look similar whether you zoom in or zoom out.
Exactly, the same pattern repeating at different scales.
And this leads to patterns, resonant patterns that pop up everywhere in how things are arranged in space, the range of energies within a system, even in how things change over time. And those patterns, the ones we often mistake for just pure randomness. Well, FRC suggests they're not random at all.
You got it. FRC proposes that this fractal resonance, these deterministic interactions between these structures that mirror each other at different scales, is much more than just a curious observation. It's a fundamental organizing principle, a kind of hidden harmony that might be at play throughout the universe.
And to capture this idea in a more rigorous mathematical way, they introduced this thing called an operator. Now, I know operator might sound a bit technical.
It might sound a bit scary to some people.
But think of it like a specific mathematical instruction, a tool designed to express this fractal resonance. It's a way to encode these self-similar interactions into our equations so we can actually work with them.
That's a great analogy. It's like we're building a mathematical language that can actually speak the language of fractal resonance.
Okay, so we've got fractal and resonance, but there's also cognition in the name. And that immediately makes me think of brains, thinking, consciousness. Are we going that deep?
Not quite, at least not directly. The authors are using cognition in a more metaphorical sense. Think of it as a placeholder for complex information processing.
So just like our brains process information through their intricate networks, FRC suggests that these physical systems do something similar.
Exactly. They process information through these self-similar resonant dynamics. It's almost like these systems have a way of thinking, in a way.
They even give some examples, like how energy levels in quantum systems can be self-similar, or the fractal patterns in neuron firing.
Exactly. It's about this inherent ability of systems to organize themselves and respond in complex ways.
Now, while connecting this to how our minds work or how AI might learn is a fascinating long-term goal, we're focusing on something a bit more tangible for this deep dive.
For sure. We're sticking to the physical world, to natural systems. The cognition part just emphasizes how FRC might one day bridge physics and cognitive science, which I think is super exciting.
Absolutely. So today's mission, should we choose to accept it? Well, it's to unpack the core ideas behind FRC. We'll look at a simple example and then explore the amazing potential of this framework in various fields. And if you're already hooked, you can find even more at fractalresonance.com.
Great plan.
All right, let's get down to business. FRC's core is this concept of vortex-like attractor dynamics with fractal scaling and resonant interactions. Wow, that's a mouthful. Can we dissect that a bit? What does it actually mean for a real physical system?
Okay, let's imagine a complex system. Within it, there are these tendencies, these patterns the system likes to follow. We call them attractors. And these attractors have a swirling vortex-like nature. But the crucial thing is, they're not simple, isolated things. They have fractal scaling, meaning if you zoom in on a part of the pattern, you'll see a mini version of the whole pattern. Like, think of a tree. The way the branches grow looks a lot like how the smaller twigs branch out.
Ah, so it's the same pattern repeating but at different sizes.
Exactly. And these self-similar structures within the system, they don't just exist on their own. They talk to each other, exchange energy or information in a way that reinforces the overall pattern. We call this resonance.
So it's this interplay, this resonance between self-similar structures at different scales that shapes the system structure, its energy, how it changes over time.
That's it. And that brings us back to those patterns we see, the ones we often mistake for random noise. They might actually be a result of this fractal resonance, not randomness at all.
Okay, I think I'm starting to see the bigger picture here. So, for example, when we talk about something like the large-scale structure of the universe, the way galaxies are arranged, FRC would suggest that their clustering might not be just random, but could reflect this underlying fractal resonance.
Exactly. Think of that vast cosmic web of galaxies, clusters, superclusters. FRC suggests this might arise from resonant interactions between those vortex-like attractors, but at a cosmic scale. We might even see fractal geometries in how these galactic structures are arranged.
And what about something like atomic spectra? The specific colors of light that atoms can emit or absorb. How does FRC apply there?
Great question. FRC suggests that the energy levels within an atom, for instance, might not be randomly or evenly distributed. Instead, those resonant interactions at those fractal scales could lead to energy levels that follow fractal statistics. You might even find energy levels clustered together in a self-similar way, almost like the atom has a fractal song of energy.
A fractal song, I like that. And then we have the way things change over time, like, I don't know, stock market fluctuations or the beating of a heart. Things that seem chaotic but maybe have a hidden pattern.
That's right. FRC suggests even those seemingly chaotic changes might actually have a self-similar structure hidden in their timing. The firing patterns of neurons in our brains, for example. They might look different at different timescales, but there could be an underlying fractal resonance governing those patterns.
Okay, so we have this picture of self-similar structures interacting in this resonant way. Now, how does the FRC operator fit into all this? What does it actually do?
Think of the FRC operator as the mathematical tool that actually makes those fractal resonance dynamics happen. In its simplest form, in one dimension, it acts on what we call the system's state function. This function basically describes everything about the system at a specific moment. Now, the operator itself has two main parts. The first involves something called fx, and this is where the fractal scaling comes into play mathematically.
So FX is like the instruction manual for building fractals.
Pretty much. It could be a function that has fractal properties itself, which ensures that the scaling behavior is baked right into the equations.
Got it. And the other part is VX, the potential. What's its role in all of this?
The potential, Vx, is what creates those interactions that lead to resonance. It often has an oscillatory, wave-like, or even fractal form itself. This sets the stage for those self-similar structures to interact and exchange energy in a coordinated way. Imagine a set of tuning forks designed to vibrate together, but across different scales.
Like a fractal orchestra. The paper mentions that this can be extended to 2 dimensions as well. Does that just mean we can describe more complex spatial arrangements?
Precisely. The core idea remains the same, but now our state function and those fractal scaling and potential terms can vary in both the x and y directions. This allows us to tackle systems with more intricate spatial patterns. Like, imagine the swirling patterns in a fluid or how a complex network branches out.
So, by applying this FRC operator to our mathematical description of a system, we can actually see how that fractal resonance could lead to those characteristic behaviors we've been discussing, like those localized patterns, energy distributions with fractal properties, or dynamics that look the same no matter how closely you zoom in or out.
Exactly right. It gives us a way to explore the consequences of fractal resonance mathematically.
Now, to make this more concrete, the paper dives into a classic example from physics, the one-dimensional harmonic oscillator. To refresh our memories, that's basically a system that oscillates back and forth around an equilibrium point. Think of a weight on a spring.
A perfect example. And in its most basic form, we know exactly how it behaves. Its energy comes in discrete packets, evenly spaced, and its wave function, which tells us the probability of finding the weight at a given point, has a well-defined shape.
Then they introduce what they call a fractal resonance potential, VFRCX, as a little nudge, a perturbation, to this simple oscillator. The first example they show, in figure 1a, looks like a wave that kind of fades away from the center.
You could say that it's an oscillating potential, and its strength is controlled by a Gaussian function, which makes it taper off as you move away from the center. The equation has parameters that allow you to adjust the wave's frequency, strength, and how quickly it fades.
Then in Figure 1b, things get a bit wilder. We see this much more intricate potential, which they describe as Weierstrass-like. Now that one definitely screams fractal. It's all jagged and self-similar.
Ah, the Weierstrass function, a classic example of a fractal. Continuous everywhere, but nowhere differentiable, giving it that infinitely detailed, jagged look. This particular potential is created by adding together a bunch of cosine waves, each with a higher frequency and smaller amplitude than the last, following a specific rule. That's what creates that self-similar structure.
So for this example, they keep things relatively simple by setting the fractal scaling term, fx, to 1, which means the FRC operator becomes essentially the standard energy operator for the harmonic oscillator, but with this added fractal resonance potential.
Right. And then the total energy of the system becomes linked to this modified operator. To see how this little fractal twist affects our well-behaved harmonic oscillator, they use a technique called first-order perturbation theory,
which in simpler terms is a way to estimate how a small change to a system will affect its properties, like energy levels or the shape of its wave function, like gently poking a stable object and seeing how it wobbles.
Exactly. And Figure 2 in the paper shows what happens to the ground state wave function that's the lowest energy state of the oscillator, both with and without that simple fractal potential. You can actually see how adding that fractal potential introduces these little ripples and oscillations into the wave function. A subtle hint of those resonant, self-similar dynamics that FRC predicts, even in a very basic system.
A simple example, but it really helps visualize how this FRC operator can bring about these complex behaviors. The paper also digs into vortex formation and scale invariance. How do these ideas connect to the FRC framework?
FRC actually draws inspiration from fluid dynamics, where you see these swirling patterns, vortices, forming spontaneously, and they can be incredibly stable. In FRC, we generalize this idea to more abstract vortices, which exist in the system's state space. These represent those stable, resonant configurations the system tends to settle into.
So like preferred states for the system, but with this swirling vortex characteristic.
Exactly. Think of them as preferred patterns of behavior occurring at different scales.
How do we describe these vortices mathematically within FRC?
The paper builds on the equations that govern vortex formation in fluids, which involve things like velocity, pressure, and viscosity. In FRC, we adapt those equations to describe how these resonant modes evolve over time. And the key is that the fractal scaling, that fx in the FRC operator, directly influences how these vortices interact and arrange themselves across those different scales. It's all about linking these stable, swirling patterns with the inherent fractal nature of the system.
And then we have scale invariance. That's a key feature of fractals, isn't it? The idea that they look the same whether you zoom in or out.
You're absolutely right. And FRC predicts that systems exhibiting this fractal resonance will also show scale invariance in their observable properties. This often manifests as power law relationships. For instance, if you look at the distribution of frequencies within the system, the power spectrum, FRC suggests it might follow a power law, where the intensity drops off with frequency in a specific way.
And if we look at how properties at different points in the system relate to each other as we increase the distance, that relationship might also follow a power law, like those correlations fading away as the distance grows, but in a specific scale invariant way.
That's exactly it. And the exponents in those power laws are linked to the fractal dimension of the system. So finding those power law relationships would be a strong indicator of underlying fractal resonance.
Okay, so we've laid out the theoretical framework, we've got the FRC operator, and we understand these concepts of vortex formation and scale invariance. But where can we actually apply all this in the real world? The paper seems to suggest a surprisingly diverse range of fields.
And that's one of the most exciting aspects of FRC. Let's start with quantum chaos. We briefly touched on how even at the tiniest scales, things can get incredibly unpredictable.
Yeah, the quantum world can be pretty wild.
Well, FRC suggests that if you introduce fractal resonance potentials into those chaotic quantum systems, you might see some really interesting effects. Imagine a stadium-shaped billiard ball bouncing around but with fractal boundaries.
Trippy.
It is. And the prediction is that while the system might still behave chaotically in a statistical sense, the actual quantum wave functions themselves could develop these intricate fractal patterns, like a hidden blueprint within the chaos.
So there's order within the chaos, at least in a visual sense.
In a way, yes. And they propose a way to test this. You could build a microwave cavity shaped like that stadium, but with fractal edges. Then you measure the specific frequencies at which it resonates. Those frequencies should reveal the influence of those fractal boundaries, acting like a fractal potential for the microwaves.
So those resonance frequencies would be like a fingerprint of the fractal resonance.
Precisely. They might show subtle patterns you wouldn't see in a regular chaotic system. Now, moving up in scale, let's talk about atomic and molecular spectra, those unique patterns of colors that atoms and molecules emit or absorb.
Yeah, like those spectral lines we see when we split light with a prism.
Exactly. FRC suggests there might be more to those spectra than we previously thought. The resonant interactions between the electrons in atoms or molecules, potentially influenced by fractal-like structures in their electron orbitals, could lead to energy levels that are distributed in a fractal way.
So those energy levels might not be randomly spaced, but could follow a fractal pattern.
Exactly. We might even see them clustered together in harmonic intervals, like notes in a musical scale. And that would affect the wavelengths of light they interact with, those spectral lines.
Fascinating. The paper mentions two tools for studying this: near-infrared spectroscopy and high harmonic spectroscopy. What can we learn from them?
Near-infrared spectroscopy allows us to look at energy transitions that are relatively low in energy, which is common for many electron transitions. It's a good starting point. But high harmonic spectroscopy, that's a really powerful tool.
How does that one work?
It involves firing a really intense laser pulse at a gas of atoms or molecules. This causes them to emit these high-energy photons at multiples of the original laser frequency. And by carefully analyzing those photons, we can get an incredibly detailed picture of the energy levels and dynamics within those atoms or molecules. We could potentially see those fractal dimensions and harmonic patterns predicted by FRC.
Wow, that's pretty high-tech. It's amazing to think that the light emitted by atoms could reveal clues about fractal resonance. Now, the paper also ventures into the realm of biological systems. That seems like a whole other level of complexity. How could FRC apply to something like life?
Life is full of self-similar structures and processes. The branching of our lungs and blood vessels, the folding of proteins, those complex neural networks in our brains. FRC proposes that it could help us model these phenomena in new ways.
Like, could it help us understand how brain activity works or how proteins fold into those intricate shapes?
That's the idea. For example, the way neurons in our brain fire might exhibit fractal resonance in their timing patterns, reflecting a deeper self-organization. And protein folding, that incredibly complex process, might be guided by fractal resonance as well.
So from the smallest scales of quantum physics to the complexity of living organisms, and the paper doesn't stop there. It even suggests that FRC could be relevant to cosmology, the study of the universe as a whole.
You're right. When we look at the universe, we see that galaxies aren't randomly scattered. They cluster together into these filaments and walls, forming a kind of cosmic web. And those tiny temperature variations in the cosmic microwave background, the afterglow of the Big Bang, they show patterns too. FRC proposes that those patterns, that large-scale structure, might have been influenced by fractal resonance in the early universe.
So fractal resonance might have played a role in shaping the universe as we know it.
That's the suggestion. And they propose looking for evidence of this in the CMB data using something called wavelet transforms. These are mathematical tools that allow us to analyze signals at different scales, looking for that fractal scaling signature.
So we could potentially see the fingerprints of fractal resonance in the earliest light of the universe. That's mind-blowing.
And finally, the paper circles back to the idea of cognition, but this time in the context of artificial intelligence. It seems like the long-term vision is to see if those principles of fractal resonance could actually underpin how our brains work, and maybe even help us build smarter AI.
Exactly. The idea is that by incorporating fractal resonance into the way we design AI systems, we might create systems that are much better at learning, recognizing patterns, forming memories, essentially mirroring the way complex systems in nature seem to process information so efficiently.
And they propose building neural networks with special fractal resonance layers. It's like trying to mimic nature's own fractal intelligence.
Precisely, trying to harness that organizing power of fractal resonance for AI. So we've covered a lot of ground here, from the quantum to the cosmic. What are the key things scientists should be looking for to actually validate FRC, to test these predictions in the real world?
The paper lays out several specific experimental signatures. First, they suggest looking for non-integer dimensions, those fractal dimensions, in the range of about 1.5 to 2.0, either in spatial patterns or in the distribution of energy levels. This would be a direct sign of self-similarity, of that fractal scaling.
Got it. So those non-integer dimensions would be like a smoking gun for fractal geometry.
Exactly. Second, they suggest looking for those harmonic energy intervals in the spectra of atoms or molecules, where the energy levels are spaced like notes in a musical scale. That would be a strong indication of those resonant interactions related to fractal structures.
So harmony in the literal sense, pointing to fractal resonance.
Exactly. And lastly, they point to power law correlations. That's where the relationship between things changes with distance or time according to a power law, with specific exponents. They even give an example in Figure 3, where they show a correlation function that follows a power law with a specific exponent. All of these are things that we can actually measure and use to put FRC to the test.
So those are the concrete, measurable fingerprints of fractal resonance. If we see them, it's a strong sign that FRC might be onto something. This is a really radical shift in perspective, isn't it? FRC proposes that instead of seeing complexity as arising from randomness, it's actually this fundamental principle of fractal resonance that might be the organizing principle across all scales.
You got it. It's a complete change in how we think about complexity.
And as the paper points out, this could have some pretty huge implications. It might reveal unexpected connections between fields that seem completely unrelated, give us new and more powerful tools for prediction, and even offer completely new interpretations of phenomena we thought we understood.
For sure. Like in quantum chaos, where we've traditionally used statistical approaches, FRC suggests those seemingly random energy level statistics might actually stem from deterministic fractal resonance dynamics.
So the randomness we see might actually be a consequence of deeper deterministic processes. That's really flipping things on their head. But of course, any new theoretical framework like FRC is going to have its challenges. The paper acknowledges that we still need to refine the mathematical side of things, like the formulation of the FRC operator and those equations describing vortex formation. And actually testing these ideas experimentally will likely require some pretty advanced techniques.
You're absolutely right. Theoretical refinement, experimental validation, and even the computational resources needed to simulate all of this. Those are all big challenges.
But the paper also outlines some exciting avenues for future research, applying FRC to specific systems in more detail, developing clear experimental protocols, and even using it to tackle cognitive modeling.
Exactly. It's a call to action, inviting scientists from all sorts of fields to jump in and explore these ideas.
So to sum it all up, fractal resonance cognition puts forth this incredibly bold idea that complexity, from the tiniest quantum particles to the vastness of the cosmos, might be organized by these vortex-like attractors that exhibit fractal scaling and interact through resonance. The paper introduces the FRC operator, and even a simple example like that perturbed harmonic oscillator shows us how those self-similar patterns could emerge. The potential applications are huge, and they've provided us with specific things to look for experimentally. It's a truly new way of thinking about complexity in the universe.
I completely agree. It challenges us to look beyond the surface, beyond the apparent randomness, and consider the possibility of a deeper, more structured origin for the complexity we see all around us.
So, as you go about your day, take a moment to look around. Do you see hints of those self-similar patterns, those echoes across different scales, in your own work, or even in everyday life? Could those seemingly chaotic or random events actually have a more structured origin, rooted in this idea of fractal resonance? It's a question worth pondering. And if you're as fascinated by this as we are, be sure to check out fractalresonance.com for more.
It's definitely a website worth checking out.
Thanks for joining us on this deep dive. Until next time.
It was a pleasure being here.